Problem number 11. Two hemispherical shells can be pressed together to form an airtight sphere of radius 40 centimeters. Suppose the shells are pressed together at a high altitude, where the air pressure is half its value at sea level. The sphere is then returned to sea level, where the air pressure is 10 power 5 pascals. What force F, applied directly, outward to each hemisphere, is required to pull them apart? Solution to problem number 11. The inward pressure force on each hemisphere is pi r squared delta p, where r equals 40 centimeters and delta p equals 10 power 5 pascal. Plugging in the numbers gives a force of 25,000 newtons. That was the answer A. And that was solution for problem number 11. Problem number 12. A space probe with mass m at point P traverses through a cluster of 3 asteroids at points A, B, and C. The masses and locations of the asteroids are shown below. What is the torque on the probe about point C? Solution to problem number 12. Only asteroids A and B contribute to the torque. Using the standard formula for torque, we have impression 1, that was answer A. And that was solution for problem number 12. Problem number 13. Two frictionless blocks of mass m are connected by a massless string which passes through a fixed massless pulley, which is a height h above the ground. Suppose the blocks are initially held with horizontal separation x, and the length of the string is chosen so that the right block hangs in the air as shown. If the blocks are released, the tension in the string immediately afterward will be T. Which of the following shows a plot of T versus x? Solution to problem number 13. This problem can be solved with limiting cases. When x equals 0, this reduces to an Atwood's machine with equal masses. Both masses are static, so the tension T equals mg. When x going to infinity, the string becomes horizontal, so equating the accelerations of the two masses gives A equals g minus T over m, which equal T over m, which yields T equals mg over 2. The only choice satisfying these limits is B. Alternatively, with a little trigonometry, you can show that the tension could be found from next three equations. Solving for T giving us expression 4, note that in general, the tension also depends on the initial speeds of the blocks. In this problem, we have made the simplifying assumption that the initial speeds vanish, and answer B is solution for problem number 13. Problem number 14. A bead of mass m can slide frictionlessly on a vertical circular wire hoop of radius 20 centimeters. The hoop is attached to a stand of mass m, which can slide frictionlessly on the ground. Initially, the bead is at the bottom of the hoop, the stand is at rest, and the bead has velocity 2 meters per second to the right. At some point, the bead will stop moving with respect to the hoop. At that moment, through what angle along the hoop has the bead traveled? Solution to problem number 14. When the bead stops moving with respect to the hoop, they must have the same velocity. By conservation of horizontal momentum, that velocity must be half the initial velocity. Thus, by conservation of energy we have equation 1. Here delta H is the change in height of the bead. Solving gives delta H equals 10 centimeters, which implies the bead slides by 60 degrees along the hoop. This is the answer C, and that was solution for problem number 14. Problem number 15. The viscous force between two plates of area A, with relative speed v and separation d, is F equals eta AV over d, where eta is the viscosity. In fluid mechanics, the Ohn-Zorge number is a dimensionless number proportional to eta, which characterizes the importance of viscous forces in a drop of fluid of density ρ, surface tension, gamma, and length scale L. Which of the following could be the definition of the Ohn-Zorge number? Solution to problem number 15. From the definition of viscosity, the units of eta are kilogram meter per second. In addition, the units of ρ are kilogram per cubic meters and the units of L are meters. As for the surface tension, it is a force per length, so its units are kilograms per square seconds. So due to dimensional analysis we have to combine from these three units proper power equation of type 1. And find the corresponding power coefficients alpha, beta and gamma. Solution will be alpha equal beta equal gamma equal 1/2. We thus conclude that square root from ρ gamma L has the same units as eta, so that choice, E, is the only possibility proportional to eta, that is properly dimensionless. This is answer E, and that was solution for problem number 15.